Hello and welcome to another 10-minute tutorial. Today we're going to be looking at how to do pH calculations. We're going to focus mainly on strong acids and weak acids. Of course, the first thing to remember is that the pH of a solution can be worked out by taking the negative log of the hydrogen ion concentration. This means, of course, that as pH goes down, the concentration of hydrogen ions will go up. It's a logarithmic scale, which means that a change in pH of just 1 unit will mean a tenfold change in the concentration of hydrogen ions. So as pH goes from 7 to 8, the concentration of hydrogen ions will decrease by tenfold. If you go from 7 to 9, then the hydrogen ion concentration decreases by 100-fold. You might remember from earlier on in school about pH being measured on the universal indicator scale using a range of 1 to 14. But the pH calculation is a mathematical expression, and so consequently it needn't be from 1 to 14. Let's take an example. If the concentration of hydrogen ions was 2 moles per dm cubed, then the pH of that solution would be minus log of 2, which gives us a negative value, negative 0.301. Or, if we have got a very alkaline solution, we might have a concentration of hydrogen ions as being low as 2 times 10 to the minus 15 moles per dm cubed. The pH here then is negative log of 2 times 10 to the minus 15, which takes us to a number greater than 14. So don't be concerned if you're doing a calculation of pH in an exam and you suddenly find a value that you've calculated as being 0 or even negative. Of course, if pH equals minus the log of the hydrogen ion concentration, it's quite probable in the exam that you might have to calculate the hydrogen ion concentration from the pH. So rearranging the equation gives us the concentration of hydrogen ions equals 10 to the power of the negative pH. This means then if pH equals 3, then the concentration of hydrogen ions is 10 to the minus 3 moles per dm cubed. However, if pH is 4.2, then of course, yes, the hydrogen ion concentration is 10 to the negative 4.2 moles per dm cubed, but you can't write that in an exam. You should write your answers always in standard form, and so putting that into the calculator gives us an answer we would write as 6.31 times 10 to the minus 5. And because you can have negative pHs, then just being careful putting that into the equation. If pH equals negative 0.2, then the hydrogen ion concentration is 10 to the negative pH, 10 to the negative 0.2, which leads us to a concentration of 1.58 moles per dm cubed. So let's do a calculation starting off with strong acids. For example, hydrochloric acid. Remember from AS that the definition of a strong acid is something that will undergo complete dissociation when it dissolves in water. So consequently, hydrogen chloride, when dissolved in water, will dissociate fully to form H plus and CO minus. Consequently, if the concentration of hydrogen chloride in the solution is 2 moles per dm cubed, then the concentration of H plus is also 2 moles per dm cubed. pH in this case is then my negative log of 2. Therefore, negative 0.301. Be careful because you may have some strong acids which are called diprotic. This means that they have 2 hydrogen ions that dissociate when it undergoes complete dissociation. So something like H2A would dissociate to form 2H plus and A2 minus. Consequently now, if we have a concentration of the acid of 2 moles per dm cubed, then the concentration of hydrogen ions is 4 moles per dm cubed. Put that into the equation, and we get a pH of negative 0.602. For weak acids, like ethanoic acid, the definition is that they undergo partial dissociation. Consequently, ethanoic acid will dissociate like this. It's an equilibrium reaction, and we need to know how far to the right-hand side the equilibrium lies to work out exactly how many hydrogen ions are present in the solution. Not every ethanoic acid molecule will dissociate. So what we need to know here, before we can do any calculation, is the acid dissociation constant, or Ka. So if we have the expression for the equilibrium, we can work out the expression for Ka. However, we're going to make some assumptions when we do the calculation here, and the first assumption that we're going to make is that the concentration of CH3COO- is approximately equal to the concentration of H+. You might look at the equation and think, yes, of course it's equal, because every ethanoic acid molecule that does dissociate will produce one H+ and one CH3COO-. But of course this is dissociating in water, and water also dissociates to form H+ and OH-. However, the dissociation of water is producing very small numbers of H+, so we can effectively leave them out for the equation. The other assumption that we're going to make is that the concentration of the undissociated acid at equilibrium is approximately equal to the concentration of the acid at the start. Again, this is perfectly reasonable, because only a very, very few molecules will dissociate. And so, say for example, we had 100,000 ethanoic acid molecules. If only one of them dissociated, we'd be left with 99,999. Which, when you round it up to 3 significant figures, is still 100,000. So let's look at a sample exam question. Calculate the pH of a 0.5 mol per dm cube solution of ethanoic acid. Of course, we need to know the Ka, and they would always give us that in the question. So of course, before we can work out pH, we have to know the hydrogen ion concentration. Taking those assumptions into play, we can rewrite the expression for Ka as the concentration of hydrogen ions squared. It's very important that you don't write this as an answer to write a question which says write an expression for Ka, because this is only one which takes into account the assumptions that we can use for the calculation of the pH. But for calculation of the pH, this is perfectly acceptable. Of course, if we put the numbers in from the equation and then rearrange the equation, we can get the concentration of hydrogen ions squared. And of course, if we take the square root of that answer, we can work out that the concentration of hydrogen ions is 2.915 times 10 to the minus 3. That's not the final answer, of course, because we've been asked to calculate the pH. So we have to do the negative log of that answer, and we get 2.54. It's quite possible in the exam that you might be asked to calculate the Ka of the acid, given all the other bits of the information. Maybe be given the pH and the concentration. But by following this tutorial, you can now recall the equation for pH. You can rearrange the equation to calculate the concentration of H+ from pH. And you can calculate the pH of strong acids and the pH of weak acids using Ka. So go to my website to try some of my test yourself exercises. I put a link in the description box below. Find me on Facebook, follow me on Twitter, and subscribe to my YouTube channel for more tutorials. Thank you.